A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 67. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience, life, and other interesting topics and fascinating ideas to educate, inspire and engineer people's minds all around the world. I'm your host Yusuf, and for this episode of the podcast I am very delighted to welcome Dr. Cemal Basaran to my show. Cemal is a professor in the Department of Civil, Structural and Environmental Engineering at University at Buffalo, the State University of New York. He specializes in computational and experimental mechanics of electronic materials. He has authored more than 150 peer-reviewed journal publications, a textbook on unified mechanics theory, and several book chapters. In this podcast, we covered Newton's law of motion and their relationship to unified mechanics theory, why Newton's laws are incomplete, Boltzmann theory and unified mechanics theory, using Abaqus as a modeling tool and defining user-defined materials, academic and career advice, 3 things to change about classical education, and much more. For updates on upcoming podcasts, projects and videos, make sure to follow me on Twitter as well as on Instagram. To join my free exclusive newsletter, engineeredmind.sh, where I share weekly science insights, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Dr. Cemal Basaran. It's really a pleasure to have you on my show today.
Oh, thank you so much for inviting me.
Yeah, finally we made it happen. So after several times of postponing the podcast, we finally made it happen. So we will talk about unified mechanics theory today, which sounds a bit ominous. Like people might ask, what is this thing called unified mechanics? But before we jump into the really extreme stuff, I would call it, can you give the audience maybe a 1 or 2 minute background? Who is Cemal? What do you work in? What does your research involve? And so on.
Okay, so I am a professor in the Department of Civil, Structural and Environmental Engineering at the University at Buffalo, which is part of the State University of New York. I teach classes in mechanics and finite element method and plasticity mainly. For the last 27 years, my research has been mechanics of electronics, microelectronics, nanoelectronics materials. And then my primary focus is developing the unified mechanics theory.
Yeah, this is super interesting. So you're basically suggesting we have Newton's law of motion and we incorporate the second law of thermodynamics into Newton's law. This is basically kind of very trivialized, but can you explain what is this thing called unified mechanics theory? Maybe in simple terms.
Yeah, so in mechanics, we have everything based on Newton's laws. Newton has 3 laws. The first law is applied forces are zero, system is stable. But the second law, in the simplest form, F equals ma. It means that if I have a soccer ball, and if I kick the soccer ball with a force F, the initial acceleration of this soccer ball will be this force divided by mass, right? Now, according to Newton's law, this acceleration continues to infinity. It never stops because F equals ma, that's it.
Mm-hmm.
But we know that this ball will come to a stop, right? Because it will lose energy. After the nanosecond that you kick the ball, the process of losing that energy is actually governed by laws of thermodynamics, right? The first law of thermodynamics is conservation of energy, and second law of thermodynamics, the simplest name is the entropy law. When Newton wrote his laws in 1687, they didn't know about thermodynamics. So there is no energy term in his equations. But however, in 1877, Boltzmann derived the mathematical form of second law of thermodynamics, and then Planck modified a little bit later on. it shows how the entropy generation in a system evolves. So essentially, unified mechanics theory takes the second law of Newton and second law of thermodynamics and unifies them ab initio level. So as a result, the equation becomes F dt times 1 minus phi equals t mv. And phi is the normalized form of the second law of thermodynamics coming from Boltzmann's derivation. And then if you go to Newton's third law, it says action F1 is equals to reaction. But here again, it assumes that the action and the reaction will never change over time. And the reaction is, for a simple system based on Hooke's law, stiffness times the displacement. Actually, Hooke's law Hooke published it in 10 years before Newton, 1678. And then Newton's law came 10 years later. However, we know that the reaction will not remain constant according to the second law of thermodynamics. Things age, degrade, again, according to the second law of thermodynamics. So again, if we introduce the normalized form of the second law of thermodynamics, the energy of the reacting system will degrade, and the stiffness, according to the second law of thermodynamics. So essentially, you end up with the stiffness multiplied by 1 minus phi. So the stiffness of the system will degrade, and the responding displacement will increase over time. And then eventually, the system will fail, of course. And the second law of thermodynamics is normalized here. It goes between 0 and 1. Now, because the second law of thermodynamics is creates an independent variable entropy, so we have to modify the Newton's space-time coordinate system, because everything in Newtonian mechanics is based on space, x, y, z, and time, but there is no axis for thermodynamics. Okay, you cannot represent a system in Newtonian space if they are not just a brand new system. Then you need a thermodynamic axis, what we call thermodynamic state index axis. So let's say, in my book, I have a picture. Let's say we have a 5-year-old boy and then 100-year-old man. So in the Newtonian space, I can put their x, y, z coordinates and then age on the time axis. Mm-hmm. So 5-year-old will be in 5 years, and 100-year-old man will be in 100 years on the time axis. But let's say the 5-year-old boy has a stage 4 cancer, and then he's expected to die soon. And then 100-year-old man is also expected to die. This thermodynamic state information cannot be represented in Newtonian space-time. You need this additional axis. Mm-hmm. On the additional axis, because everything goes between 0 and 1, both the 5-year-old boy and then 100-year-old man will be both at 0.999. They have the same coordinate, even though they have different coordinate on the time axis, but they have the same coordinate on the thermodynamic state index axis. Because this additional axis is linearly independent, then the derivative of displacement along x or y or z with respect to entropy is not 0 anymore. Because in Newtonian mechanics, if you look at the Lagrange equation or Hamiltonian or whatever you write, the derivative of displacement with respect to entropy is taken as zero, because there is no such an axis to take derivative. But in unified mechanics theory, because you have an additional axis, which is linearly independent, so derivative of displacement with respect to thermodynamic state is non-zero. So as a result, you add additional terms. But on the other hand, you don't need any phenomenological terms in the equation. Like, for example, if you write the dynamic equilibrium equation, it is mass times acceleration. Let's write it in Newtonian mechanics. Mass times acceleration, damping times velocity, stiffness times displacement equals some force. Right? Now, mass, we know what it is. The stiffness, we know what it is. Now, damping is a phenomenological empirical parameter. Because Newton's F equals ma does not have a dissipation term, we measure the damping dissipation in the real system and then use that empirical coefficient in order to introduce dissipation into Newton's equilibrium equation. In unified mechanics theory, we don't need the C term. That term is automatically included in the differential equation because the thermodynamic state is defined by the thermodynamic equation of the material. We don't need an empirical coefficient because the thermodynamic state, the thermodynamic state index phi, is calculated from the entropy generation in the system, and entropy generation in the system can be calculated from the thermodynamic fundamental equations. So that means we have to derive the fundamental equation of the material.
I see. Okay.
And then we don't need the C.
That was beautifully explained, Cemal. I appreciate it so much. I understood it even without seeing the picture of your book or even a script. Now the question that a person might ask, because I liked the analogy between the boy and the old man. We will talk about materials maybe now, material degradation, fatigue, or maybe, I don't know, if you can even describe cracks with it. When we talk about materials, how can we apply this unified mechanics theory, and what can we determine by this theory when it comes to fatigue, for example?
Yeah, I mean, it doesn't have to be a 5-year-old human. If, let's say we take two cars, okay? Any X brand car, okay? One is driven as a taxi in a very bad road, okay, with lots of bumps, and then one ridden by some professional on a nice highway. Even if they have the same age, let's say they are both 2015 model, okay, that doesn't mean that these two cars have the same thermodynamic state, okay, because one has experienced significant entropy generation because where it is driven, how it is driven, and then the other one will be in much better shape. It is why you can have one car 2000, whatever year it is, last three, like in New York City, taxi drivers usually replace their cars after 3 years because it just falls into pieces. So, on the other hand, I replace my cars every 15 years. So the time axis doesn't say anything about the thermodynamic state of the car. Only thing that matters is how much entropy did that car generate during those 3 years. Because the taxi in New York City generates more entropy than my car in 15 years.
That makes absolute sense, yeah. I think it isn't even a bold statement to make that you basically are saying that Newton's law per se aren't wrong, but are basically incomplete, if that's correct. Right, Cemal?
Yeah, they are incomplete, but there is a reason they are incomplete, because when 1687 Newton wrote these laws, they didn't know about thermodynamics.
Yeah, that makes sense. Any other applications we might think of, maybe not thinking about cars, maybe any other applications that the audience might be interested in when it comes to unified mechanics theory, Cemal?
Well, if we are using Newton's laws, then you have to modify them. Wherever you use Newton's laws, you use them in biomechanics, or you use them in wherever you use Newton's laws, because laws of thermodynamics apply to everything. Mm-hmm. They are not applicable only to humans and cars. Laws of thermodynamics, universal laws of motion apply to everything. So some people, there was a conference last year questioning the applicability to social science. It is a little bit outside my comfort zone, because social systems are open systems. The laws of thermodynamics are written for closed systems. But there are people who are working on applying this concept to social systems. But anything that is a matter, either liquid or solid or a gas, are governed by laws of Newton and laws of thermodynamics.
Yeah. The things that you have briefly described here, very compactly described, and when you made an example about unified mechanics theory, I bet there's so much more in your book, because I've had a look at it. What else is covered in your book? And maybe make some kind of a bit of advertisement for your book if they want to get it. Maybe let the people know what's inside of your book and what they can expect from it.
Yeah, the main point in the book is, until recently, most people thought that the Boltzmann's formulation, entropy formulation, was only for gases. Mm-hmm. Because the paper was written in German, and most people don't speak German, nobody in the English-speaking research world bothered to read it. People were just... And the book, his first paper was written in the title of the book was Theory of Gases. So it was assumed that it was just for gases. But I have spent last 30 years, initially experimentally, later on mathematically, to prove that actually Boltzmann's formulation is not for gases. It is for gases, solids, liquids, for everything. Actually, Boltzmann himself finishes his paper by saying this in his paper, but nobody bothered to read it, I guess. In my book, I go through his derivation, and then later with his derivation was continued by Max Planck. And then I annotate line by line to prove that this derivation is for solids and gases and liquids, not just for gases. Mm-hmm. It is applicable to all materials. Now, he does use term gas in some places. He runs mind experiments, but I explain that if I change that gas to solid and then add friction, in the final equation, in the derivation, nothing is changing. So the book provides the mathematical proof of Boltzmann's formulation for solids and liquids. It is not just for gases. So that is the main mathematical proof in the book. And then I have 3-4 chapters of examples. The first 4 chapters are the derivation, you can say, of the mathematics. And then last 4 chapters are the examples.
Very, very interesting. And I will put the link of your book, Cemal, down in the description so people can check it out. Of course, when we have these equations, some people might be so, let's say, risk averse to implement them onto a system. So when we talk about modeling and go on the abstraction level, down or up, however you want to define it, and want to use computers or machines to solve these equations, How did you personally approach this? Like, what did you use? FEA models? What type of modeling tool did you use? Was it ANSYS, Abaqus? Maybe you can explain a little bit more around that.
We have been using Abaqus here for a very long time because ANSYS didn't allow us to put user-defined elements and user-defined materials until recently. And of course, when you use material nonlinearity, or if you want to introduce a new element, then you have to put your own element and you have to put your own material. So we use always finite element method, but we use UMAT and UL and use Abaqus as a front and back and as a solver, because if you use Abaqus, Abaqus is just solving Newton's equations. Like for example, even if you do damage mechanics in Abaqus, it is just phenomenological. You have to have some test data and then you have to have some polynomial, but you are not really doing anything physics-based. Just you have already the test results and you put that to degrade the stiffness. But in our case, we have to have a subroutine to calculate the thermodynamic fundamental equation, and then at each Gauss integration point, and then send it to Abaqus, calculate the stiffness matrix, and then we use Abaqus as a solver, and then we get the nodal displacements, and then go forward. So we always use Abaqus here, but we modify it because there are many things Abaqus cannot do. Like for example, we studied electromigration in electronics for a long time. So in unified mechanics theory, you have to, it is not just displacement, but essentially the entropy, because it's an independent axis, it becomes a nodal unknown. Okay? Abaqus cannot do that. So you have to trick Abaqus into, like for example, you can have displacement and temperature at one node, right? It will be U, X, Y, Z, and then temperature. Well, we take that temperature as additional node and then use it for the entropy part of the differential equation. So yeah, we have been very, very successful with Abaqus, both solving verification problems or also large-scale problems for the industry. We have an electronic packaging lab here. We have worked with every or most of the major electronics manufacturers in the world. We have solved real problems using this concept and have been very successful.
Very interesting. Thanks for sharing that. And I think the question will come for sure once we posted the podcast. So I'm asking it inside of the podcast. Have you faced any other bottlenecks, Cemal, when defining these UMAT routines and maybe using Abaqus when it comes to unified mechanics theory? Anything else that maybe was really a pain to get started with?
Well, every time do nonlinear analysis with finite element method, time becomes a problem. Okay, because your time steps determine the increments, determine your accuracy, and the systems sometimes are very large. As a result, the solution time becomes really a challenge. So our biggest challenge have always been the solution time. And we have a supercomputer here, but however, it is not easy to parallelize these subroutines. Like for example, Abaqus is not very good if you want to parallelize a nonlinear problem.
I see.
It is very, very primitive. Very, very primitive. So even I don't know how many nodes they have, but they have lots of processors on campus. But it doesn't mean anything if your program is still running on a single processor. Mm-hmm. Okay, if your stiffness metric is still sitting on one node, you can have the fastest computer in the world. Yeah. Unless the equations have been completely nonlinear, decentralized, and each one goes on to 1 million nodes. So Abaqus is very, very poor in terms of parallel processing for nonlinear problems. So that is one of the biggest challenges.
Very interesting insights. And maybe I want to make a jump, because for me it's always special to see that you said you worked on this for 30 years.
Yes.
This is very interesting to me, because for me personally, I'm someone who likes to explore different topics. For me, it's very interesting to have a look at your career, Cemal, and maybe give your maybe 2 cents or like life advice in general, or career advice to people listening to this podcast. Maybe they're inspired by this podcast. They want to delve into unified mechanics theory. Maybe just out of the blue, maybe get started, like career advice, maybe work-life balance, which we talked about before the recording. Maybe add your 2 cents here. And I think it's very interesting for younger students listening to this.
Yeah. Well, I was born in Turkey. I grew up there, and then I came as a graduate student to MIT with a scholarship. So I started from zero. Very, very poor background in Turkey. But if you want to succeed, there is one rule that you cannot essentially avoid. That is, you have to love what you do. Mm-hmm. You have to love what you do. If you don't love what you do, okay, if you see it as a burden, if you see it as something that you have to do to put food on the table for your family, pay the bill, very, very unlikely you will succeed. You have to love what you do. And I am 61 years old now. My advice would be for somebody very young, life is really, really very short. It passes much faster than you can ever imagine. Just find something you love and then do it. And then it doesn't matter what it is. You will succeed. You will definitely succeed if you do what you love. And then you will be much happier. Like, for example, this semester I'm not teaching anything, okay? I teach next semester. So that means I don't have to come here, right? Mm-hmm. I can stay home and watch TV. But I come here before everybody else, and I leave after everybody else, because I love what you do. If you say, what are you doing? I am working 2nd edition of my book, which I just signed a contract with the publisher. Because to me, it is not a job. It is not like I come here so that I can put food on the table or I can pay my bills. To me, this is like something I really love, I enjoy. So that what you have, every person definitely has something that they love. They must have something. I don't care if it is cleaning, okay? Go do cleaning and you will be the biggest cleaning mogul. You will start a cleaning business and you will be a cleaning multi-millionaire. Mm-hmm. But don't do something you don't like.
Yeah, I think this is beautiful advice. And I think there is even a quote from Naval Ravikant saying, if you find something that looks like work to others, but is play to you, then you basically won in life. And I think this is basically summarizing what you just said, which I think is very, very beautiful, Cemal. Maybe one point I want to talk about is also how you came to the US, because I think you also mentor students or mentored students in the past when they want to go for a postdoc position to the US. Any advice from your side, moving from one country, whether it's Turkey or any other country, to the US?
Well, coming as a graduate student is much easier if you are a good student. Essentially, you coming as a graduate student to the US is very easy, assuming you are a good student. There are many scholarships. either from the universities or from foundations. But coming as a postdoc from another country is more difficult because American universities prefer to hire US graduates as a postdoc. There are exceptions, of course, but it is more difficult. So if you want to come to US, it is easier to come as a master's student or a PhD student. But you can always, of course, apply for a postdoc too if you graduated from a very good program, a very well-known university overseas, then you can have a good chance of getting postdoctoral position. Another reason it is more difficult to come as a postdoc because it is more difficult for us to get a visa for you as a postdoc. But for students, it is very easy. F1 visa, it is not a work visa, it is a different type of visa. So it is also easier for the university, that is why.
So very good input. Thank you so much, Cemal. And when it comes to financial aid, where would you personally apply for yourself when you would do it again, all over again? Because I think a lot of people or students struggle with this, like where can I get financial aid from?
Yeah, so in order to get financial aid, make sure that your credentials match the university you are applying, okay? If you are not top of your class, you didn't graduate from one of the top universities, you have not won a national scientific award in your country, don't apply to MIT. Okay, you're very, very unlikely they will give you an assistantship or any scholarship. And then, so your credentials has to match where you are applying to. And then look at the rankings, pretty much. The rankings are not perfect. There are some very, very good universities in number 50, but follow and then make sure that you apply at least 10 universities that are comparable to your credentials.
I see.
Okay, comparable to your credentials. Now, most universities in the US will not accept applicants with 3.0 or lower GPA. But actually 3.0 happens to be a high GPA in some countries. In that case, you will have to contact the university, find a professor who will be your advocate in the admission process to explain that, yes, your GPA was 2.9, but you were valedictorian of the university, and then you have to prove it with a letter. Then you will have a better chance. But as a rule of thumb, most schools require 3.0 to be able to apply for a master's, and then 3.5 to be able to apply for the PhD program.
I see. Very good input. Thank you so much, Cemal, for this. One thing I want to talk about, and I think you're a bit biased here, because do you think that classical education is dead, so that it moves more towards the digital world? Do you think the classical lecture is kind of dead, or how do you see it a bit more differentiated? Like,
yeah, I think the way we teach has to change. Classical education, we are not able to communicate with the, I guess you can call it Z generation, because this educational system was created when there was no internet, there was no computer, there was no TV, okay? You had to go to a classroom and then teach people on the board with a chalk. But however, now students are looking at a screen all day on their smartphone or a computer. They are watching these videos all day. So they learn differently. They are continuously interacting with the video. But however, when I teach in a classroom, where there are 200 students, and you have to sit there without falling asleep, if you are lucky, and then listen to some guy talking, 30 meters away. I think this educational system has to change. In my opinion, it is dead.
Mm-hmm. Very interesting. If you had the power, if you could change 3 things, Cemal, what would you change? Teaching-wise, educational-wise in general, what would you do?
Well, first of all, we have to stop this going to the classroom and then teaching on the board. It has to be like a video game, and then every week the whole class plays a video game on the topic, and then they have to be active learners. When you are playing a video game, you don't watch it. You have a joystick, you have a mouse, you are always doing something,
mm-hmm.
right? And then you are using your senses. You are actively engaged. You are not sitting in a chair all the way back and looking at some guy writing on a board with a chalk. So I would teach by means of video games,
mm-hmm.
and everybody has to be playing the game.
Point number 2 and 3, what else would you change?
And then number 2, of course, bringing people is still very important. Like I wouldn't leave it only on the video games, because when I started school, one professor told me, you are going to learn from other students, then you are going to learn from me. So human touch is still very important.
Mm-hmm.
I would still have more communication in person among the students that will force them continuously give a presentation or interact with other students. Essentially, in our system, professor just lectures like a Sunday lecture. I think this method comes from the church. You go to the church on Sunday morning, the priest lectures, and you sit down, you take the sacrament and go home. I think it comes from there. But this method has to change. Students have to be talking, interacting together every day. That is very, very important.
Yeah.
Now we don't have that. And then the third thing I would change is our exam method.
Mm-hmm.
Some students are exam performers, some students are not. I know some very, very brilliant students who would do very poorly on the exam.
Yeah.
And then I know some students who do perfect on the exam, but if you ask them, give them a task where they need to be creative, they have zero creativity.
Mm-hmm.
But on the other hand, if you ask them to memorize 50 pages and then give them an exam, they will solve, because they will memorize all the problems in the book. They will solve it and they will get 100. But if you give them something from outside the book where they have to be creative, they get 0. But our system is geared towards one type of learner.
Yeah.
If you are good in memorizing, if you are good in exam performance, we award you. If you are creative, we penalize you. So the system is very discriminatory, very, very discriminatory.
Yeah, I think when I remember back, it wasn't called Turkey back then, but a few hundred years ago, you know exactly what I mean. There were schools where they took students and basically were teaching them their strengths. So if someone was very strong in mathematics, this teacher would basically work on the strengths of the students and not so much on the weaknesses, having big classrooms, and he would pick the students one by one and teach them in their strengths. Maybe you remember that, like, I read it somewhere. It was very nice to me when I read that. Very interesting approach.
Yeah, our teaching is not inclusive, very exclusive. We essentially teach for one type of learner, and then everybody else is excluded.
Yeah,
different type of learners.
Yeah, I would agree on that. Do you think that people also have forgotten to think critically for themselves and just take everything as given? So when you as a professor say 1 + 1 = 3, students will be like, okay, that's true. And then they write it down and memorize it. Do you think that's the case, or becomes more?
Absolutely. Yeah, I'm telling you, I think our system, educational system, the lecturing system comes from the church, because like schools like Harvard, when they first started, they were religious institutions. Okay, so when the teacher or the professor walks into the classroom and tells something to the students, it is like the priest. It is like a word of God. It is true. First thing I tell my students, in my classes, don't believe anything I tell you. Don't believe anything I tell you unless you can go ahead and prove it yourself. If you believe everything they tell you, then we would still be, Earth is flat. Okay? Earth is flat, and then everything would be there. Don't believe anything I tell you. Go prove it yourself. And don't believe anything that you read. Prove it. Derive it. Does it make sense? Question everything. Question everything you hear, you see. It is how we can go forward. But our educational system does not encourage that. Our educational system, I give you 20 pages. This is true. Go memorize it. And then I will ask you 3 questions from these 10 pages.
Yeah.
I don't ask you something creative. I don't ask you something, come up with something new.
Yeah, I see what you mean. I would fully agree on that. Whether it's now education system, media, or politics, I think thinking for yourself sometimes can really help rather than following the collective consensus. Yeah, I think I'll leave it at that without jumping into politics right now.
Well, essentially, it is the educational system is very conservative, very, very conservative. It doesn't change quickly. Essentially, you talk to the professors, well, they say, oh, I studied this way. I am fine. Why should we change it?
Yeah, I can remember back when I was in my bachelor's in mechanical engineering, when the lecturer was so smart that he still couldn't break down difficult topics into smaller chunks, which makes them more easy to digest for students who didn't really get it. And I think that made the lecture so boring. So I think you, Cemal, and we have kind of the opportunity to teach students, whether it's online or in the classroom, in a better way, and maybe make the education system a little bit better. I think that's the step into the right direction.
Well, look at the best example is Bill Gates or Zuckerberg. Bill Gates, he was a sophomore at Harvard. He created a project for himself. Okay, so I'm going to write a subroutine for this computer that will be an operating system. And he says he was so much into writing that operating system that it became his life. He couldn't even sleep. Okay, and then he wrote the most successful program in the history of the world. He never got his 4-year degree, bachelor's degree from Harvard, right? Now, that means that Harvard did not give him a degree because he didn't finish 120 credit hours in Harvard.
That's what you mean.
In my opinion, Bill Gates should be given the bachelor's degree for doing 120 hours of work in one topic, writing that subroutine creatively. Do you understand what I'm trying to say?
Of course, yeah, definitely.
Same thing with the Zuckerberg. He was a sophomore at Harvard. He got obsessed with writing Facebook subroutine, right? And then it is one of the most successful social media. Now, he had a lot of challenges, of course, when he was writing it. Now, again, he didn't get a bachelor's degree from Harvard because Harvard is very conservative. You have to finish 120 credit hours. You have to take course in this and this and this and this. No, why cannot he just take one task do it, and then get a bachelor's degree.
Yeah.
If I were Harvard or president of Harvard, a student like Zuckerberg or a student like Bill Gates will get their bachelor's degree after 4 years.
Yeah. I think even, I'm not sure if both did it, but I think they got that degree afterwards, years after they even quit.
No, they gave them honorary doctorate.
That is true. But I was reading something. Could be, but I get your point, Cemal. So that's that. Yeah, it was a very interesting discussion, Cemal.
But there are many people like these two individuals. I mean, Zuckerberg and Bill Gates are very famous, but there are many, many people who quit school and they just work on something very new, very creative, and become immensely successful, and they never get a degree from this established system.
Yeah, I see what you mean. Yeah, they're strictly following the rules, basically, what's on paper. Yeah, I see what you mean. Very inspiring discussion, Cemal. Is there anything or any closing remarks from your side? Any inspiring words, tips, and tricks?
No, life is too short. Do what you enjoy. Believe me, do what you enjoy and you will be very, very successful.
Awesome. I love it, Cemal. Thank you so much for this interesting discussion.
Thank you for inviting me.
Finally, we made it happen, and I can't wait to publish it. And of course, as I already promised, I will put the link down to your great book in the description so people can check out Unified Mechanics Theory and delve a bit more into it and learn more about soccer, kicking a ball, or a 5-year-old or 100-year-old man. So again, Thank you, Cemal. And
thank you.
See you maybe in a
second.
Thank
you very much.
Thank you.
Thank you. Bye-bye.